Hi, welcome to another edition of Linear Algebra. Today we are going to start talking about the details of eigenanalysis. We are going to derive eigenvalues, eigenvectors, and eigenspaces of a matrix. Let's go ahead and take a look at this very important topic. So these are the topics for today. We are going to limit ourselves to small case of 2 by 2 matrices to get a good practice on the concepts, and then we gradually go up to more difficult cases of 3 by 3 or 4 by 4 and so on. So what was the topic? The topic was we were looking for we started with a square matrix. We have a square matrix, let's call it M. We say if we take the matrix M and multiply it by some vector x, out comes another vector, let's call that y. Okay. We said we want to get a visual impression of what is happening, and the challenge was, well, even in the smallest case, x has two components and y has two components, so between these two we are looking at four numbers. So the problem is really a four-dimensional problem, and none of the problems you have done so far in any of your calculus classes has four components to it. Definitely didn't try to graph such a thing. So we have a new approach to this issue. How do we graph this? We pick a coordinate system, in this case our R2 two-dimensional coordinate system. On that coordinate system we have one vector x, so x is going to be some pair of numbers x and y. We take M, 2 by 2 matrix that are given to us, multiply by this x, out comes another vector y. It could be perhaps like this. So this is the vector y, and that has two components as well. Now if you change x, well, of course y is going to change correspondingly. Move this around, that one is going to move around. There is a special case, and the word special is just that word eigen. So the word eigen that we see over and over again, it simply means special case. So the special case here is that x and y line up. X and y line up, meaning they are both on the same line. So same line means if, for example, if this is your vector x, and then the vector y will be in the same direction. It's also possible that in opposite direction, that for example you might have x like this, and then y would be in that same direction. So when that happens, x is called an eigenvector. X is called an eigenvector. The line on which both of these two are sitting, either this case or this case, that line is going to be called eigenspace. Okay, the line is called an eigenspace. This vector is called an eigenvector. The degree by which the vector stretches or shrinks is going to be called eigenvalue. So eigenvalue is your stretch factor. this. You have to take y divided by x. That's the stretch factor. We use this Greek letter for that. We call that lambda. So special case is that m times x out comes something that's a multiple of x. I'm going to write it like this for a reason we are going to see later on, that x is multiplied by lambda of whatever it is. We looked at a very nice app last time. Let's go ahead and take a look at that again to see what is it that we are referring to here. So this was this nice app from a Wolfram demonstration project. You go there, look for eigenvectors in 2D. You have to download it, and then you have to also download Wolfram Player to be able to play with that. It's a kind of a large download. And then, well, you click on these things to get the control mechanism. These are the coefficients in the matrix. The matrix that you see here, matrix A, you see has the components 1, 2, 4, 3. You can, after you click on these things, you have controls here. So for example, you can increase your components. So for example, you saw that from 1.0 I went all the way up to 1.9. Let's go back to what it was. I lower it back toward a nice number 1.0. So you control on click on this to open or close the control mechanism, and then you play with the components of a matrix. Then you come here, the red vector, just like in our lecture over there. This let me make this a bit smaller maybe. Okay, so if I play with this thing, let me bring the both of them in the same view. You notice that around this location blue and red line up, and you see here they are not lining up. Let me make it small so you see they're not lining up here, but I go and feel my way toward a location where they do line up. When they do line up, well, if you stretch it, they still line up. Any of them could be considered as your eigenvector. We typically choose situations where the numbers are nice, if that's possible. Aside from that, once you find one of them, any multiple of that is still an eigenvector. Then if you go around in the page and feel your way, follow your nose, you might be able to find others. For example, you see here they again line up. They line up, they are in opposite direction. Opposite direction simply means your lambda is negative. So I have to actually make a correction here. If it is, I go back and rewrite that in a more precise way. But the stretch factor could be negative, in which case means your vector flips to the other side. Okay, our objective today is to play with this concept. We are going to start with a very simple example that I'll give you the input vector, and you tell me what's the stretch factor. Second case, I will tell you the stretch factor, and then you give me the vector itself. The third case is the mature case that I don't give you anything other than the matrix itself, and you find both the red and that's the eigenvector and the stretch factor lambda. So that is how we are going to gradually get used to this topic. So let me go ahead and make a correction here. So if you say y is equal to lambda times x, that lambda is the eigenvalue, which is the stretch factor. So that y I wrote lambda times x, or x times lambda, either way. Okay, just like that in that little app, let me start by a simple matrix. Before I go to that, let me emphasize that we made a stipulation that this vector x should be something other than 0, because of course matrix times 0 is equal to 0 times any number, and that does not reveal anything for us. That's going to be considered a trivial solution and essentially useless. So I'm going to take a matrix M, just like that little app there, 1 2 4 3. To get us started, I'm going to give the x and ask you to find lambda. So I say, for example, x is equal to, in this case it turns out, let's say 1 2. So now say assume an eigenvector x of a matrix M is given, and what we want to find is find the corresponding eigenvalue. Okay, so again, the idea, let's go back to understand what's going on here. The idea is I'll give you the vector. I give you the vector like we gave here 1 2. I give you the vector 1 2. So I tell you where the red is. So it is kind of like 1 2. Now if you want to make it exactly 1 2, you have to stretch it. Now my blue is going to get out. Okay, so I cannot enlarge. So this is almost 1 2. You have to have a very steady hand to get this thing right. The blue vector becomes large, gets extended out of the page. You see it's 5 10. That is 5 times bigger than what the input is. Well, we want to figure that out by computation. How do we do that? Very easy. Take M multiplied by X. So 1 2 4 3 multiplied by 1 2. That's very easy. So we multiply row with the column. What do we get? 1 times 1 plus 2 times 2 adds up to 5. 4 times 1, 3 times 2 is 4 plus 6. That adds up to 10. Now we ask, is there a special relationship between the output and the input? In what sense? Is this the stretched version of that? Yes, it is stretched. The stretching factor is 5. If I take 5 and multiply with my input, the output becomes this. That is what is special about the situation, that the output is a multiple of the input. So in this case, we say for x equal to 1 2, lambda does turn out to be 5. The stretch factor is 5. So this is the simplest type of a problem where the eigenvector is given and we are to find the eigenvalue. The flip side of this thing is just the opposite. That is, I'm going to give the eigenvalue and ask you to find the eigenvector. So how does this go? If I convince my page to roll up and down. The vertical rollers in OneNote does not behave as supposed to, but anyway, so let's do this in reverse. We said so we want to do this thing in reverse. m is equal to, again, 1, 2, 4, 3, and lambda is equal to 5. Find the eigenvector. You kind of have to forget that we already seen it here, but suppose we haven't seen this problem, and that's how we are starting, that I tell you what this number is, you tell me what that vector is going to be. So here I start by saying mx is supposed to be x times lambda. This time I don't know what x is, so I just put numbers, parameters a and b. This is supposed to be a times b times lambda, that is 5. So let me just write lambda and then I convert it to numbers in the next round. So my m is 1, 2, 4, 3 times ab. This is supposed to be ab, and then times 5. Well, let's just go ahead and multiply and convert this to a regular equation. How do we multiply? Again, nothing new here, so just multiply. So I have 1a plus 2b. On the right hand side is 5a. Then I have 4a plus 3b. On the right hand side I have 5b. Well, it's just an ordinary equation. Bring everything to one side. So minus 4a plus 2b is equal to 0. In the second equation is 4a minus 2b is equal to 0. If the given information is correct and we have done everything right, have not made a mistake, we end up with a situation that kind of very loud and clear is something special going on again. That word special here, something special going on. Well, what is special here? In 2 by 2 cases, each equation is the multiple of the other one. Okay, so here we have minus 4i plus 2b is equal to 0. If you take that equation, multiply by minus 1, you get this. So the two equations are really same equations written in two different ways by multiplying by different numbers. That makes it easy for us to actually find non-trivial solution because we are not forced for a and b to be 0. You have infinitely many choices here. Easiest choice you can pick is like a, you can pick it to be 1 and b will be 2. Of course, you could have taken a to be, say, 10 and b will be 20. So you have other choices, but if possible, we go to smallest set of whole numbers if that's possible. So if I have my a and b, that means I have found my eigenvector x is a turned out to be 1, b turned out to be 2, and that is our eigenvector. So again, what was the process? The number is given, eigenvector we don't know, we write a set of parameters like a and b or x and y and such, or x1 and x2, whatever style you want to choose. Multiply both sides, bring to one side, you have a system of equation. Previously we called it homogeneous. There is something special about this system that allows us to pick non-trivial answers, and we are going to talk about this more extensively later on. But right now, for 2 by 2, special means these two equations are multiples of each other. So that is this case. Let's go ahead. This one was a little bit more complicated than the previous one. So let's try one more practice here. Again, I go after the same 1, 2, 4, 3. And this time I give the other eigenvalue. We remember in that picture we went and followed our nose, and here we found our way that, like, if I go around here, almost here, I get another eigen situation. The input and output, same size in opposite direction. It simply means the multiple is -1. So my input flips to the other side. Both of them are on the same line. Okay, both of them are on the same line. Well, this is experimental way of finding it. You go around until things line up. But how do you do it? By computation? Well, that's what we are learning. So lambda is equal to -1. Find the eigenvector. So that's another practice. We haven't seen the numbers, but so I try again, exact same as before. 1, 2, 4, 3 times. Now my eigenvector, again I call it AB, and this is AB times, let's write in parentheses, so I write again 1a and 2b, and right hand side is -a, and then 4a plus 3b, and right hand side is -b. That's my equation. I bring everything to one side. I get 2a plus 2b equal to 0, and 4a plus 4b equal to 0. Notice the eigen special situation. The two equations are really same equations. This one you can think about double of that, or that one is half of this. It's the same equation. What are values for a and b? Very easy. Any two numbers that are negative of each other will do. So for example, I take a or say take b to be say -1, and a will be 1. Of course, I could have taken a to be -1 and b to be 1, just as good as that one. Or you can take it 10 and -10. Any of them is as good as any other of them. And the only thing you are not allowed to use is to say 0, 0. Of course, 0, 0 does fit here, but that's not going to give us an eigenvector because we are avoiding trivial answers at that stage. So here I have x. So which one of these things do you want to pick? Like say 1 minus 1 is eigenvector, or -1, 1, or 10 minus 10. Any pair of opposite numbers would do, other than 0, 0. Okay, once we are here, let's go and draw the picture. So in most of exercises you are going to be asked to draw just what we drew here. So we had one, the first one we had here was 1, 2. So 1, 2, you just draw 1 and 2. So this is 1, 2. In the other one, 1 minus 1, so this is just as good. 1 minus 1. If they ask you to draw m times the eigenvector, so like in that app these things were red, and when you multiply them, it's going to go all the way there. It was 5, 10, for example, and in this case minus 1, 1. Then they ask you typically for the eigenspace. So there are two eigenspaces here. Well, if your hand is steadier than mine will help. So these are the two eigenspaces. And then you can, for example, denote what the lambda was for each of them. Lambda for this one was 5, lambda for this one was -1, and what else? These are our eigenspaces. So eigenspace is a line or something else we are going to see later on that contains your collection of eigenvectors. In that case, we do include 0, 0, just so that there is no hole in that eigenspace. Okay, so these were the simplest examples. Now we are going to remove the training wheel. So in example 1 here, this is training wheel, and mom or dad actually holding a bicycle still. So when I give you the x and I find the land, if I give you eigenvector and ask you for eigenvalue, that's the easiest. You just multiply, see stretch factor or shrinking factor, and you're all done. Next, I take my hand off the wheel, so probably a bit more complicated, but still you have the training wheel. I give you something, I give you the lambda and ask for the eigenvector. You have to multiply, bring everything to one side, solve that equation. So if the equation was bigger, well, you have that machinery. You remember we did have a machinery, huh? We had well, here, this was our big helper there. So you do have that one to help you if the system gets bigger, but you have a system to solve. You go ahead and solve it, and you find all the missing entries. If it was a 3 by 3 matrix, you have more work to do. 4 by 4, gradually you'll sense the amount of work that's involved here. Okay, now next up, remove the training wheels. Okay, remove the training wheels. Okay, so you do all of it. Nobody's holding you. You have to do somehow this computer is acting strange. Okay, so next up, I neither give you the eigenvalue nor eigenvector and ask you to find all of it. So that problem becomes substantially more complicated, by orders of magnitude more complicated problem. For 2 by 2 still easy, just like stuff that you have done in algebra in high school, but by the time you get to 3 by 3, it's going to be kind of upper level algebra, high school, like very tough algebra. And as the size of the matrix gets bigger, and this problem has a tendency to become algebra intensive. Still, of course, most problems that you're going to see in the textbook, they are all designed so that they don't pose so much challenge, but be ready to go back to high school algebra, those difficult equations and so on. Okay, so next problem up is that I give you the m, which was what, 1, 2, 4, 3, and ask you to find everything. Find eigenvalues, eigenvectors, eigenspaces. So in these problems, there's a whole list of things to be done, and well, you have to do all of them. And because they become extensive, you have to be systematic, careful, do everything, write everything nicely so that you don't make any mistakes. And it becomes a bit high stakes, because if at the beginning you make a mistake, then well, everything goes bad after that, hard to recover. Okay, let me remind you of a very important topic that's going to come up in this section over and over again, and we are gradually going to build this thing up so that we'll have quick machinery for approaching this thing. So we have to go back to some issue we had a while back with respect to homogeneous systems. Let me start by a simple example so that you see what the issue is. So we are going to do a quick review of something that is an essential ingredient here. So I'm going to give you two sets of systems and ask you, tell me what's the essential difference between the two of them. One of them, say, let's write some random numbers. Let me see. Let me write this. 2x say plus 3y is equal to 0, and say 5x plus 4y again equal to 0. This is system 1. Another system I give you is 4x plus 6y equal to 0, and then say 10x plus 15y equal to 0. Okay, very simple 2 by 2 systems, both of them homogeneous. Now I said there is a fundamental difference between the two of them. Okay, there's a fundamental difference between these two. I want you to discover that for yourself. You're very capable of doing that right now. What's the big difference between these two? And then that is going to be building block of everything else we are going to do from now on just about every problem we are going to do for all the remaining lectures in this chapter. So here, take maybe several minutes, or perhaps just a few seconds. What's the difference between these two? So no cheating here. Go back to pause this thing, figure it out, come back. Okay, so I'm assuming that you did pause and coming back here. Suppose I want to solve this. You can do it by that heavy machinery of Gaussian elimination or whatnot, but let's just do it very simple like you would do it in high school. What would you do? You say, well, let me eliminate perhaps x, or let me eliminate y. Suppose I want to eliminate y. So I take this thing, multiply by 4, multiply this one by minus 3. So I will have 2 times 4x plus 3 times 4y. This one I'll have minus 3 times 5x minus 3 times 4y equal to 0. And add the two of them. Well, when you add them, of course, these two cancel. That was the idea, how to cancel them. And then here you factor, you say 2 times 4 minus 3 times 5 x is equal to 0. Now you notice that this is 8 minus 15, and that is not 0. So the only way this can be true is that x has to be 0. You go ahead and do this thing a second round, and this time eliminate x. Okay, I leave that to you. You eliminate x, you find out, well, y has to be 0 too. So the only way you can keep this equation happy is to have x equal to 0 and y is equal to 0. That's the only possibility, which you could see from outset. Of course, if x and y are 0, the equation is satisfied. But what we showed that under no other circumstances would the equation be satisfied. We have to pick 0, 0. How about here? Suppose we apply the same trick. We say, okay, let's cancel y. So I multiply this thing by 15 and multiply this thing by 6. Is that right? Multiply this by 15, multiply this by 6, so that when I add them up, the y goes away. But what do I get? I'm going to get this time 4 times 15 minus 6 times 10 times x equal to 0. Does it mean that x has to be 0? Well, no, because luckily this is 0. This is 60 minus 60. So these numbers are special now. Again, that word special showing up. We have arranged it so that these numbers are in such a special proportion. This becomes 0. That means x is free. X can be any number you want. So you can choose x as you like and then decide what y is going to be. No, y is not going to be arbitrary once you decide on what x is. So what is causing this? You look at this thing, you see these two equations are really the same equation. These are both multiples of 2x plus 3y. This one you have doubled it. So if you take in 2x plus 3y equal to 0, if you double it, you get that. If you multiply it by 5, you get this. So if you satisfy this equation, both of these are satisfied. How can you satisfy that? So let's choose some nice numbers. I take x to be, for example, like what? 3, and y would be, say, minus 2. Or many other choices. You could have taken this to be 6 and this would have been 4, minus 4, or you could have taken this on minus 6, this one would have been 4. All of them are good, so we pick one of these. So okay, this is a sample that shows up everybody else. The thing about eigenvalues and eigenvectors is that is how they are laid out. That special number eigenvalue is arranged so that our equation becomes like this, so that this factor becomes 0, so that x is free, and so that we get an answer other than 0, 0. Okay, so that's the foundation of what is eigen here. What is special here is this. Okay, so let me rephrase this discussion. If I have ax plus by equal to 0 and then cx plus dy equal to 0, if I have an equation like this, surely x and y equal to 0 is an answer. That is, we are going to consider trivial answer. For having non-trivial answer, that factor has to be equal to 0. What does it look like? This is 4 times 15 minus 6 times 10. That is AD minus BC. Well, we have seen this creature before. We have called it determinant. We are going to have a much bigger discussion on determinants. A determinant of who? Determinant of these 4 numbers, A, B, C, D, which form our coefficient matrix. We say if AD minus BC is equal to 0, then we will have non-trivial answers. Otherwise, we are stuck with the trivial one, that is x and y has to be 0. So if this quantity is not 0, like here 2 times 4 minus 3 times 5, this was of course 7 or minus 7, that's not 0, so you're forced x to be 0, y 0. In this case, that factor became 0 and x became free. You choose x free and then y is determined and so on. Okay, that's the foundation. Now let's see. So again, going back, I have m to be 1, what is it, 1, 2, 4, 3, and we are after lambda, and x, let's call it, say, what should we call it, so that let me call this thing x, y. So I'll have 1, 2, 4, 3 times x, y. That should be x, y times lambda. Okay, I neither know what's here nor what is there. That's why the problem is much more mature type than what we had before. How do we go? Well, multiply on the left 1x plus 2y. Multiply on the right is lambda x. Make sure you write your lambda correctly so you don't confuse it with your numbers and such. 4x plus 3y, lambda y. Now this whole thing is a new creature. New creature because I never saw product of 2 unknown quantities before. It never showed up in any of my equations. So you have to get used to this situation. What do? Bring everybody to the left and put them next, similar things next to each other. So I write like this: 2y is equal to 0. And this one 4x and then 3y minus lambda y equal to 0. Okay, so I intentionally wrote it this way. X is common. I factored it. 1 minus lambda x plus 2y equal to 0, and the second one is 4x plus 3 minus lambda y is equal to 0. So I emphasize again, just be ready that you're looking at a new scenery now. Okay, this is a 2 by 2 system. I want a solution other than, so I don't want x, y equal to 0. I don't want that. That's a trivial thing. I don't want to end up in a situation that x and y are 0. What did we say? That's only possible if the determinant of the coefficients is 0. That's only possible if your system looks like this, with these things proportional. If you pick your lambda randomly, you end up with this kind of situation and you end up with zeros. So that's a random situation. This is a special situation. This is a special situation. We can afford non-trivial answers. So you want something other than this trivial answer, you need to have determinant of 1 minus lambda, 2, 4, 3 minus lambda to be 0. Okay, I hope everybody followed the reasoning. That's why you are in this class, to follow the reasoning. But if you want a shortcut, something on the exam, you want to move quickly. How do you quickly come here? It's very easy. You have, here's your 1 2 3 4 1 2 4 3. Lambda is subtracted from the diagonal entry. So if you want to bypass all the stuff in the middle, I don't recommend it, but if you're in a rush and you have to, well, here is the shortcut. You take your matrix, you subtract lambda from the diagonal, and what was the determinant? Determinant is simply product of these two minus product of these two. Determinant is AD minus BC. So what is, put a parenthesis around your entries so you don't make a mistake with signs and such. So 1 minus lambda times 3 minus lambda minus 2 times 4. That has to be 0. So I put the parentheses to avoid sign mistake. We said these problems are expensive problems. Expensive meaning one mistake, 10-15 minutes is lost. You have to start all over again. So it pays to be careful from beginning, and then just a little bit of extra care, even though it takes time. That's fine. Spend a little bit of time to be careful with respect to your steps. So what do we do? Well, by now we are in the territory of easy problems in, say, Algebra 1 in high school. You just multiply stuff out. So 1 times 3 minus lambda is 3 minus lambda. Minus lambda times this thing is minus 3 lambda plus lambda squared. So again, and minus 8 equal to 0. Right in civilized order, lambda squared minus 4 lambda, 3 minus 8 is minus 5 equal to 0. So what now? We are in that sweet topic in algebra called quadratic equation. Okay, so you have done plenty of these things in high school. So that's why your pre-calculus is prerequisite of this class. You factor this. 90% of the problems you're going to see, factorization is going to be very easy. Well, 10% you have to work a little bit harder, and let me remind you when you have to work harder. If you have to work harder, you have ax squared plus bx plus c. That's your quadratic equation. X, if you want to bring the big guns, let me see, you remember what's in the radical? Of course you do. B squared minus 4ac, denominator is 2a. So if you need to bring the big guns, that's the big guns, but usually small guns is enough. So it's what's the factorization? Lambda, looking for two numbers such that the product is -5. The other option would have been +5 and -1, but that leads to +4, so that doesn't work. So you practice your factorization. You practice factorization for cubic too, because that's going to be coming up. Okay, now the punchline. Doesn't look like a joke, but here is our punchline. Here are two numbers, lambda equal to 5, lambda equal to -1. Isn't that what we did here? On that case, we gave it to you, so that's why we called it on training wheel. I give it to you, and I give it to you, and then you find the other things. But here, you go ahead and find these two. Now, once you found this, what do you do? Well, once you find it, then you are back into this problem. You have the 5. How do you find the eigenvector? You go and find it. You have -1. How do you find the eigenvector? We just did that. So you have to go ahead and find. So you say this one leads to x or v or whatever you call it. We had what? We had 1, 2. Is that right? It was 1, 2. If I remember correctly, it was 1, 2 here. 1, 2, 1, 2. And the other one, 1 minus 1, or any other representative from that class. X is equal to, so 1 minus 1. When you go on website, they help you not to confuse one with the other one. Typically, they label it like this. They say larger eigenvalue, and then you fill in the blank, and then smaller eigenvalue, and then fill in the blank for that one, and then of course you also answer how about the eigen. So this is of course your eigenvalue. You get your eigenvector, and you get your eigenspace. For eigenspace, you can draw it, or so drawing it will be just like we did with these lines. That's one style. The other style, eigenspace, at this level, simply all the multiples of this. So if I take 1, 2, multiply it by some parameter t, this is going to be all the eigenvectors including 0, 0. That's going to constitute the eigenspace. Another style that you show up on website or your homework and such, it's written like this: span of, you remember the word span, set of all linear combination of this, which means just the entire line. So in this case, this would have been written t1 minus 1. Make sure you see the syntax and follow it so that you don't get into the issue with your software. So eigenspace, so style number 1, style number 2, style number 3, you just draw it however it's needed. Okay, so these were some of the most basic examples of eigenanalysis. We went after most common situation you're going to see. Now they are all sort of special cases that come up. Perhaps we don't crowd this lecture with all of those. Those special cases have to do with special cases of quadratic equation from high school. So let me see, you remember there were 3 cases. Okay, so back to high school. If you have ax squared plus bx plus c equal to 0, And then you say, well, here is my beacon, minus b plus or minus radical b squared minus 4ac over 2a. That all sounds very nice, but what? But the difficulty shows up depending on what is under this radical. If b squared minus 4ac, which gets to have a nickname, they call it discriminant because it discriminates between several cases. If your discriminant is positive, well, that's a normal situation. You have two distinct roots. Like what? Like what we had here. We solved it and got two answers, 5 and minus 1. They are distinct, means just different. They're just different numbers. Well, what do you mean by that? Well, special case. What if delta was 0? Such as what? Suppose I had x squared plus 6x plus 9 equal to 0. You see, there's something special or troublesome here. This is when you factor it, what do you get? Both factors look like each other. And then you get two identical roots. You want to do it this way, you say minus 6 plus or minus 6 squared minus 4 times 9 times 1 over 2. Well, peculiar thing, maybe you should call it peculiar. In the radical, you get 0. So it's minus 6 plus or minus 0 over 2. Better not drop this thing because you're going to lose track of that. This is one answer is minus 3 and the other answer also minus 3. And that's going to be source of quite a bit of headache for us later on. Identical answers is a source of, if you might call it interesting, might call it troublesome situation. So identical roots. Notice we didn't see that situation, our problem here. Or what's a third situation? Third situation, what if this was negative? Well, what if this was negative? Well, I will have negative on the radical, I'll have complex numbers, and all of that is going to come in. So in this case, I'm going to get two complex conjugate roots. Let me remind you again from high school. Suppose I had x squared plus 6x plus 13 equal to 0. Well, if you sit down and try to factor it, it doesn't look easy to factor. If you try ordinary numbers, nothing works, so you might throw your hand up in the air, but there is a factorization. To find it, it's better to go and use the big guns. Say minus 6 plus or minus 6 squared minus 4 times 13 times 1 over 2 times 1. So it's minus 6 plus or minus 36 minus 52 over 2. It's minus 6 plus or minus square root of minus 16 over 2. So here is a whole can of worms in here. It's minus 1 in radical. We write it as I in mathematics. In engineering they like J because I is reserved for current in electricity, one way or another. This becomes, well, here we write 4I. Your book writes as I. So what happens here? No, so you say minus 6 plus or minus 4I divided by 2. Next, factor first, then simplify. That's a common mistake. Student ignore that and their problem falls apart. Factor first, then simplify. Minus 3 plus or minus 2I. So in that case, if that shows up in my problem, then my eigenvalues will be complex numbers And then eigenvectors are going to be complex numbers, and there's going to be a whole set of problematic things to learn about complex numbers. When they become complex, unfortunately we are going to lose all of our pictures, because nothing here, I cannot incorporate I into this picture. So once that shows up, we essentially give up on the idea of drawing anything, because it becomes too complicated, and we just go with that. Okay, so we reviewed some basics of solving quadratic equation. We noticed that there are three scenarios, two distinct roots. This is the most common thing we see, but we have to be aware of existence of the other one, identical roots. And this one, we cannot brush it under the carpet and say, oh, it's complex, let's throw it away. It's not significant. Actually, it becomes very significant for us later on too. All activities in physics that have to do with rotation, they can be represented by a matrix as well, and those matrices always act like this, so we cannot rule out complex numbers. They're just part of things to come up with. So we are going to do a few exercises in the future lectures, but for now the only case we have done in our examples is this one, and I'm going to postpone the other two cases into a separate lecture. Until then, good luck and God bless.